Hi everyone. I have to say that I am overwhelmed with this many people in the audience. I highly appreciate that. Thank you very much. So this is Hossein. I work in UC Louvain in Belgium. That's the French Catholic University of the French-speaking Catholic University of Louvain. This is joint work with Peter. Now, today I'm going to give you a new paradigm for programming distributed systems. That's, I do apologize if this is a bit different from what you saw in the abstract and in the titles. What you came here for is in the paper, so don't worry, I'm not really putting something completely new in. This also is in the paper, but not with this focus. So I am Iranian, and that's an Iranian ironsmith giving that hot thing good shape with the hammer. That I expect you guys to be the ironsmith. That would be our idea, and those are your feedback. So please hammer us as hard as you can to give us the good shape. So distributed systems, and in particular distributed systems programming, I have identified three creatures in there. I'm going to speak about them for you now. So let's first of all make sure that we are all on the same page. A distributed system is a collection of network-connected nodes that, to the user, look like a single system. Now, our observation in distributed systems is that their execution is rather mostly functional. And I'm going to give you an example, but just to first tell you what that means. It means that if you take a look into the execution, the reductions are mostly of the kind arrow lambda, and that's anything that can be modeled using like pure lambda calculi. Very few in the reduction are of the form squiggly, which are things that cannot be modeled that way. Now, so if you take a look into the executions, you would notice that it's these long successions of lambda reductions interleaved with very small number of squigglies. That's great, that's the good, but it's not explored yet. Now, being at TFP, we all know about the good properties, those powerful properties of pure functional programming. You get like idempotence, referential transparency, equational reasoning. Everyone knows about them here. And well, you can even stay in those and do complete distributed systems programming. The thing though is that you can't do everything, but you can do important classes of them. So pipelines, for example, some of you might be familiar with, and like durable functions. This is a new Microsoft type. So they have identified like 5 categories of the common patterns of doing distributed systems programming, and function chaining is one of them. And you can do that in complete lambda successions. The bad is that, well, these squigglies are unavoidable. Generally, any time you need input, you need something that is unavailable in advance, or it requires interaction with the outside world, outside the closed world of yours. You have to use squigglies. And that's examples of that are input from the user, input from the database, well, modulo some simple things, and timeouts. And these are real things that you do need in distributed systems. So there is bad things. Now, distributed systems programming is currently practiced on top of this mindset. Side effects are inherent in distributed systems programming. Right? The conclusion that is made out of that is that we have to give up purity. There is no way you can do that. Yeah? Wrong. That's wrong. Both of these sentences are in fact wrong. Right? Now that wrong understanding has led people to the wrong assumption in terms of the formalism, the squiggly things that I showed to you, that everything in distributed systems programming is a squiggly. And therefore you see, imperative programming all around. Distributed systems, loads of imperative programs. That's ugly. That is ugly. Right? Now, something that you don't quite get in good, bad, and ugly is the hero. We have a hero too. Ta-da! Prop, this new paradigm of ours, and I'm going to give you what that stands for, is a new paradigm for programming distributed systems in which we would like to unify the execution model that I showed you, which is mostly functional, with the programming model. So we would like to have a programming model in which the programmer mostly does the programming in a functional, in a pure functional way, and is aware of those situations where they are making squigglies, right? Now, I'm going to now give you an example of prop, and then we'll see more. So here is a distributed system, very simple one, a server S, a set of clients C1 to Cn, and the way we speak about this, just very quickly, is this thing. That's invoking the function server on the node S, invoking the function client on each and every one of the nodes C1 to Cn, and those run concurrently. Now, so here's what happens. The clients send their requests to the server. That goes through the port of the server. And then that forms a stream for the port. Requests get processed using that, let's say, F server function, and then the results get back to the right people, to the right clients. Now the clients might then again do some processing on their side. That's the F clients. Right? And then you get another feed of requests into the port. Right? That loop goes on. Things to notice. First of all, F server and F clients can be these huge, completely pure functions. Millions of lines. Right? So it's all lambda successions. The other thing is that the server function is also pure. It's not changing any resources, right? There is one thing. The client sends things to the server. That is going to change the stream of the port, right? That bit is not pure. That bit is a squiggly. But everything else is actually a lambda succession. The other thing is that, so we have noticed that, and we have noticed that the fact is that this impurity is only for the server node. The fact that I send something as a client to the server does not produce any impurity observable to the rest of the clients. It's only an impurity, a side effect that is observable to the server. So in order to model that, we have come up with this thing called a pure block, something of this form. Right? And what this is saying is that the function client is pure for the entire world except S. Right? Now, so more into pure blocks. A pure block is actually a promise that we currently check at runtime, but it can also, at least for the simple situation that we at the moment have in our semantics, can be checked at compile time also. It's a promise that these guys in its belly are not going to have any side effect for the nodes mentioned here. Now we have different notations for what comes upstairs. So you can say that I am pure with only these guys and the rest of the world is safe. Is unsafe, or the reverse. I mean, it really depends on the context which one you want to choose. So prop builds on 3 pillars. A, different pieces of code might have different purity properties. That's the reason why pure blocks can have different granularities. Right? So that's pure blocks. 2, side effects are relative. That's the question of who's watching. Something that is pure to me might be impure to one of you. Right? Who's watching? It's a matter of, it's a good question to ask. 3rd, oh, come on. Oh, it's back, okay. It's a question of what is there to watch, right? Now, sometimes, if you're interested in particular resources, you might still be completely pure, right? Now, there is this question, for example, that when you want to consider the fact that who's watching, right, you may realize that certain pair of requests might be observationally equivalent to, let's say, the server, right? I'm not sure how visible that is, but up here on the tilde, there is this S that we put, and this is something extra, right? It's a matter of who wants to see this observational equivalence, right? The other thing is the resources. So, for example, it might be that 2 requests are observationally equivalent to S so long as its local heap is the interest, right? That gives us prop, which is piecewise relative observational purity. So, what are the benefits of prop? I'm going to speak in terms of the pillars that I told you about. So let's say that this is your imaginary piece of distributed systems program. Oh, come on. Now, so we have a piece of program that is running on A1. That's the line 1. And another piece of program that is running concurrently on A2 and probably more. The scheduler knows it when the execution of what comes upstairs makes it to this red part. Right? Now, remember, there is a promise here. These guys will not manipulate the resources that are observable to A1 to AN. Right? That's our notation. Well, it's a list comprehension. Most of you are familiar with, but I should have put it there. So that means that the scheduler can inform, whilst it is executing that bit, that A2, well, it should inform, or it can inform A2 to AN that they are safe. Right? For example, they can go without worrying about race conditions. something very, very important in distributed systems. Right? So that was for pillar 1, which is the benefit that you get from the pure blocks, but it doesn't stop there. Right? There is more beauty to come. So how many of you are familiar with this thing called flaky tests? Very good. Thank you very much. Thank you. Thank you. So, yeah, tests are called flaky when you get non-deterministic results out of repetition of the same test, right? This is something very real. So 2 very recent studies, one of them was published by almost the end of the year, last year, but show that this is a major problem in the not just distributed systems, but any kind of software development. And now in distributed systems, people have thought about or possible courses of action. How long do I have? 2 minutes. 2 minutes. And so, like in 25% of the situations, they request fixing the order of events. Unfortunately, this is not a solution in distributed systems. And what we propose is that if the results are different, but they're still observationally equivalent to the right node, that's good. We're fine. We're fine. We've observed the same thing. So that's about the moral thing that you told us about, like yesterday. What was it called? You had a conference on I can't recall the name.
Quality of trees? Yes, that's right.
No, there was this conference. It was a particular model of testing, right?
The metamorphic testing.
Yeah, the metamorphic testing. Now, what is new with respect to that is this upstairs A, right? So it's a matter of who's observing. Now, there are other benefits that are in the paper. So distributed garbage collection, model checking, speculative execution, and mock testing. Now, I have to remind you, this is just hope. We haven't still done the job, right? This is just hope, yeah? And we would like you guys to give us the good hammer for us to get into the good shape. Questions, please.